Okay, thank you, Aida. I guess you can hear me. And so I'll, in the following previous speakers, I hope this will be a somewhat forward-looking, historically oriented but forward-looking talk. Here are the topics that I'd like to talk about. The first section is something that we've heard a number of times in the talks. The fundamental fields, quarks and gluons, reveal themselves. Here it'll be from the point of view, somewhat a slightly different point of view, leading up really to the high PT kinds of scattering of partons. Then I'll talk about jets from QCD, following quarks and gluons into the final state. A bit about factorization. We've heard of these things, of course, in previous talks. If there's time, I'll talk a bit about using ideas of universality and summary and for the coming years. So this is an overview of some of the origins and the fundamental concepts of perturbative quantum chromodynamics, with the emphasis here on perturbative, that are still, I hope, relevant today, with a few recollections from my own personal path in QCD, which, well, some people have said the story is not totally, somewhat interesting. So anyhow, the fundamental fields reveal themselves. There's protons and neutrons and all of these resonances that grew over the years. And so there were, as we've heard, different ways of thinking about it. It's say in the late 1960s. That hadrons might be composite, yet irreducible, and bootstrapped, leading to strings that we heard from this morning. A wonderful story, a blob comes in and other blobs are created as an electron hits a hadron. Or they could be, instead of composite yet irreducible, composites of indivisibles. And that, to some extent, the quark model, where a number of partons come in, they're hit by an electron, and then groups of partons are created, and the electron goes off. So the question was really, and that was all the successes of the quark model. So are these little stars real? And of course, the problem there was confinement. Okay, so I'm learning to do this. Well. Oh, somehow it's I think here we have Keith's talk, and I'm moving along in Keith's talk here. It's a wonderful picture of Drell and Yan. Yeah. Okay. Well, let me go back here. Let's. Okay. Yeah. It's just. Yeah. Yeah, now we're back. It did it the first one, so hopefully it won't do that again. Okay, so this was in the light of quantum electrodynamics and G-2, which of course is a great subject of interest right now. And at that time, around 1970, Nature made its choice. And really the background of that is current algebra, where these stars provide currents and could match on to a theory like Yang and Mills. If you added the idea that the currents, using the ideas of Yang and Mills, led to vector fields, and the vector fields, if you had the right symmetries, would lead to forces. And here's a quote from Sakurai. This is a very profound idea, this vector fields, currents, vector fields, and forces, in that order of implication. Perhaps the most profound idea in theoretical physics since the invention of Dirac theory. At the same time, there were experiments at SLAC on elastic scattering, where dipole-like form factors indicated that whatever these sources of charge were in the proton, they were small and, well, strongly coupled because of their confinement. So deep inelastic scattering, as we've heard now a bunch of times, that was really lightning strikes. The electron sees these constituents as spin 1/2 point particles. Here's the picture. At the initial state, we have a proton, the electron comes in. There's our J, a current, which is provided by these composite particles. The electron bounces off at an angle, and you can tell a lot by measuring how they're distributed in angle. And whatever happens in the final state inside this blob and another baryon and some mesons are created, all this stuff doesn't matter as much. It's as if the whole process were almost just the elastic scattering of the star here, which is represented by a point-like quark. So in this context, the strong force seemed weak, almost irrelevant to the electron that scatters. The quark parton model of Feynman followed, Bjorkane, Pascos, that we've heard about again, where to some extent we can ignore all the interactions between our stars here after the scattering by a single parton, and introducing this variable, the momentum transfer squared, over this energy loss in the appropriate frame, we get to the parton model that the cross-section on a proton is the same as a cross-section for a parton with the appropriate charge, which already gives us all these extra windows, times the probability to find that parton. And what goes on afterwards doesn't really matter at all. So when all this happened, quantum field theory analysis was ready. And it was ready with these currents that, of course, we heard about, current algebra. So electromagnetic current correlators for any field theory with a coupling alpha S of mu was known that taking moments with respect to this variable x, which you could determine just by measuring the electron, would give you moments of correlation functions. And the rough form that they took is of a matrix element of a local operator here, ON, where n is reflecting the moment that you take, times something you could calculate in that perturbation theory. And this was pre-QCD, as people have noted already in the talks. So however, in perturbation theory, if it's a renormalizable theory, you need to introduce a scale. So the scale here is, as usual, mu, and with the analysis of Wilson, Brandt, Preparata for these example, Frischmann, Christ, Hauslocker, and Mueller, we get to this relationship between these observable moments and these operators times coefficient functions. But this mu that we choose, the scale of the coupling, is our choice. Nature doesn't care how we decide to do this calculation. So starting with this form involving the cross-section, or cross-section of any kind, with a factorized form here on the right, just a product of two operators, both of which depend upon the scale mu, because we couldn't define this matrix element without the mu dependence. We can use separation of variables and say, oh, we can find the mu dependence of just from our calculation of this perturbative part. And separation of variables tells us it has to be some constant, an anomalous dimension, times this alpha S of mu, the coupling in that theory. And this quantified the paradox that we found, that somehow the partons were acting as though they were weakly interaction. So this weakly interacting, that it really requires this alpha S of Q to be small, and the strong interactions are weak in deep inelastic scattering. Let's see. Well, all right. Let's see if we can get it to. Oh, we're having a little problem again with advancing the the slides. Well, gee whiz, this is the part we've heard, I don't know, about 5 times already. I'd like to get through with these slides.
You just like to sing.
Am I doing something wrong here by maybe leaning this way? Well, yeah, there it is.
Yeah, the issue is sometimes because we're using Zoom, it takes over and overlays. So all you have to do is just click on the mouse here. A little bit over there. So.
Oh, you mean here?
Yeah.
Okay, so if it freezes, try clicking there. Okay. So this was just at the time when quantum chromodynamics came. I guess it must be 50 years ago. Because I remember the name of the conference, you know. So here were the quarks and gluons. It was just the right set of currents, the right kinds of forces. You can compute, if you think about it, one way of thinking about it, the time dependence of a quark emitting a gluon corrected by a quark emitting another gluon, emitting a gluon seriously, and then taking back the first gluon. And you can, if that's inside some region, say, of radius c times t, you can get the time dependence. And by calculating that, you get, of course, the famous QCD running coupling here at the one-loop example. So asymptotic freedom then gave scaling, and of course, these were, well, I guess it's really 1973. So the idea was that near a parton, a quark, the force is weak, and that gives scaling. Far from a quark, the force becomes strong. You get an infrared strong coupling, which perhaps could describe quark confinement in ways that we heard about already. And then from the point of view of the experiments in deep inelastic scattering, by the time a struck quark gets far enough away to feel the strong force, the electron is long gone. So its distribution is already determined. And by then, the other remaining quarks reassemble into hadrons over a different time scale, typically called lambda QCD. Whoops. So in a few years later, we got this beautiful DGLAP evolution, and a picture of evolution. And really, the picture here we show the basic idea. An electron comes in, exchanges a photon with a charged parton, which is then scattered. And then as you go to higher values of renormalization scale, corresponding to the higher values of momentum, a larger momentum transfer, it begins to resolve states that appear that have more quanta and of which are larger in number but are shorter lived. The larger the momentum transfer, the shorter lived states you can resolve, and there are more such states. And it's the fact that you keep getting more and more of those states that leads to evolution. And asymptotic freedom, which describes this particular process well in deep inelastic scattering, is, of course, a big deal, and here we are today to show it. I mean, asymptotic freedom, in some sense, to QCD is what elliptical orbits were to Newtonian gravity. On the other hand, it's a beginning, not an end, as, of course, we're here to discuss. For Newtonian gravity, it just took a year or so before people realized, hey, the big problem, it works well for the moon, great. But what if you throw the sun into the bargain? All of a sudden, you can't solve the equations anymore. You know it's out there, you know it's working, but what does it really mean? How long does it take to get control over that? And as a matter of fact, now 350 or whatever it is years later, say 350, say for gravity, it was 1660 something, we're like still grappling with that, okay? And here we are at 50 years, so I think we've done pretty well in 50 years, but not so much better. Like a lot of really interesting work was done on the three-body problem within 50 years. And that was without Zoom. Okay, so the idea was, all right, so this is our three-body problem. How do we observe confined degrees of freedom? So the goal is, to some extent, another, and I promise you this is my only other fractional equation, that nuclear physics be to QCD, or QCD be to nuclear physics, what QED is to chemistry. Right? You keep getting better and better pictures, but it still keeps giving you surprises. But at the time, really, one was asking, can we study the particles that give the currents, that is the quarks, give the forces, the gluons, expand in the number of gluons? That's perturbation theory. And remember, when we're looking at this exchanged photon, as the energy was increased, or the momentum transfer increased, we are seeing states with more and more particles because those states are shorter lived, but we're able to resolve them better and better as we go to larger and larger momentum transfer. So really, perturbation theory is a language for that, to bring these particles, these degrees of freedom to life. On the other hand, bound state scattering is complexity and strong forces. So at the time, this is the historical part, maybe the whole thing is, all right, does this make any sense at all? And believe me, I'm kind of old enough to remember being told this makes no sense at all. In some sense, it was like atoms before the observation of radioactivity, and molecules before the explanation of Brownian motion. Hey, these are great ideas, and they do help you think about it, but don't expect me to believe this is real. So that brings section 3, which is jets from QCD, as the situation stood back then, following quarks and gluons into the final state. So what we were trying to do was really learn to calculate with this then new theory. So you could take this contrast of correlation functions versus the S matrix. And of course, in condensed matter, correlation functions is you live with that. That's really your main tool. The S matrix was something that was invented because it's a black box. This is like really hard. All you can see is what you put in and what you get out, so don't expect to look inside. The correlation functions are great if your two operators are close to each other, like this j of x and j of 0 in the first equation. And if it's a physical quantity, you can choose your renormalization scale to be 1 over the distance. And then if you have a coupling that decreases in the distance, suddenly becomes a weakly coupled problem, and you can use perturbation theory and generally get a better idea. The S matrix, however, even at high energy, is pretty hopeless because it always comes in with the scale of the masses of the initial state and the scale of the produced particles in the final state. So you get mass scales, and if you think about, well, maybe the m pi, mp, but then I wanted to do perturbation theory, didn't I? What about mq? And the gluon? Well, it can't really have 0 mass, can it? Well, maybe it should in perturbation theory. But still, it's only a problem of the ratio m over q. So there's some hope that if you think about things in terms of what does it mean to take m to 0, or how does that relate to q going to infinity, you might get some insight. So this was the way things stood, I think, looking back. Were we doomed to compute only correlations of currents? Were we forbidden to look inside the final state, to see the states that connect those currents? The current where you put up energy in, the one that describes energy flowing out. Or would it be possible to see quarks and gluons? So now, here we have something that was already out there. In fact, to an extent that I didn't really realize until a few years ago, the structure of final states, from cosmic rays to quark pairs. Particle jets, the word jets to describe particles goes way back, really back to the 1950s. So here's a quote from the Philosophical magazine, by an article by B. Edwards, who had emulsions and was looking at emulsions. The average transverse momentum resulting from our measurements is pt equal 0.5 BeV over c. Now you know it's really historic, right? And table 1 gives a summary of jet events observed to date. I mean, when I saw that, I couldn't believe it. So the idea was that there was a limited transverse momentum in the secondaries of hadronic collisions from cosmic rays. So what about quarks and E plus E minus annihilation, where in perturbation theory you could compute them? So here's the picture. You have electron-positron coming in, annihilating, producing quarks that come out. And then the question was, is this going to give us 2 sprays of particles, or is it going to give something else? Is it like 2, yeah, okay, so that's it. So it's an extension of the parton model. Quark electron scattering to E plus E minus goes to QQ bar. So the conjecture was that the way to think about it, and in many ways it was, that the sprays of particles would be characterized by a PT cutoff, which was what had been seen in cosmic rays. So but it would give you, because on the left you already determine what direction your sprays of particles are going to go by the lowest order, kind of parton model cross-section, it gave a prediction for the angular distribution, 1 plus cosine squared theta, and we saw a little bit of that in Torbjörn's talk historically. So here from a paper, a very famous paper, Drell, Levy, and Yan, because of our cutoff, the distribution of secondaries in the colliding ring frame will look like 2 jets. So here was a question you could ask of QCD. Would the final state look like this? And in fact, of course, it did. And here's the famous paper, Gail Hansen et al. In 1975. So a little bit more about jets from QCD, and here the story gets a little bit personal, how I came to study E plus E minus final states. So I came, my studies at the University of Maryland was in echoes of the old and stirrings of the new, you might say. I studied complex analysis of scattering amplitudes with an advisor, not Davisor, but the advisor, Alex Strocht, and perturbative form factors at the same time in Yukawa models with Joe Sucher and Ching-Hung Wu. And actually, one of the papers I read was a paper by Ciaffaloni, which played a large role in the work that I did on the subject of form factors as a student. Then I went on to Illinois, where I had my first postdoc and had a lot of discussions with topics of the time with Xiaojun Chang and Jeremiah Sullivan. And one of the topics we talked about was the data from the Cambridge Accelerator on E plus E minus, the ratio of E plus E minus to hadrons divided by E plus E minus to mu plus mu minus. And here in 1973 or 4, it was I think 73 data, was as a function here, it's a function of S, so it goes up to at 16 here, that's a 4 GeV, center of mass energy. And you could see the cross-section just like going up, and so what's going on? Here's data that we've seen just in Aida's talk. This data is easier to find now online. This is what it looks like now, and that 4 GeV range is right around here. That's where the charm quark had come in. But the charm quark hadn't been discovered yet. It wasn't totally clear what was causing this. So there was discussions about could it be that the cross-section increases with energy as some kind of power or something like that. And everybody that I talked to there knew better and said, no, it's not going to happen that way. And shortly it was clear that we were seeing the cross-section respond to the charm threshold. So out of this came an abstract question, that is to say, at least for me, with an abstract answer. And the question was, by analogy, talking about what happens to cross-sections when you radiate, and you get more energy and you can radiate more particles whose masses may be much less than the energy you have available. And how are we doing? Oh, not so bad, I guess. So here in QED, typically you have the first correction to some scattering from state A to state B involves a function which happens to be fairly universal. It would be some beta AB, which is a function of the energy divided by the mass of the electron, times the log of the mass of the photon divided by the momentum transfer. Well, of course, that's the log of 0, so it's kind of a big correction. Now, the solution to this problem was known since the time of Bloch and Nordsik in the late 30s, and that was that the way to think about it is you have to sum over all photons emissions up to some energy resolution, which you parameterize as epsilon times the momentum transfer. And when you do that, you don't try to see all of the photons because you can't see all of the photons. You replace this log of m gamma over q by a log of 1 over epsilon. And unless epsilon is fantastically small, this correction is completely under control by giving up the complete knowledge on the final state. And this was the impossibility of resolving arbitrarily soft photons, which nevertheless carry a small but finite amount of the energy, really a small amount of energy related to the momentum transfer. And here, there's some words here. Because individual photons can be emitted with arbitrarily small energies, there will always be the possibility that some photons will escape detection. Okay, so this is where I learned the concept of the energy resolution. I mean, I learned it in the QFT course, but it didn't quite come home. Anyway, so the question was, could something like this happen? Well, there were two things. What happens to when the mass of the electron goes to 0? Then that function beta that multiplied the log of 1 over epsilon itself has a divergence, which went by the name of a mass divergence, because the only mass around in QED was the electron. And then again, there was this QCD. What about that if we took a quark mass to 0? And of course, it was all in the light of the famous analyses of Kenosha and Leon-Nauenberg. Now, here, somebody else was thinking about this also. And this is from the very famous paper, Soft Gravitons and Photons, and it's a footnote. And I actually only saw this recently. He talked about the Kenosha to Leon-Nauenberg. You have to average over initial states, sum over final states, and get a finite transition probability. And he makes a notice, these ensembles include not only indefinite numbers of very soft quanta, but also hard massless particles with indefinite energies. And I remain unconvinced that transition rates between such ensembles are the only ones that can be measured and need be finite. Well, after some thought, going back to now my time in Urbana, it turned out that, not surprisingly, and especially in the light of Kenosha to Leon-Nauenberg, epsilon is not enough, the energy resolution, but with an extra angular resolution delta. I'll just call it delta here, it works. This is the impossibility now not of observing arbitrarily soft photons, but a pair of an electron with a photon, both massless and traveling right on top of each other. How would you know the difference? But what was really going on now in retrospect, it changed the focus in thinking, if one were thinking about this as somehow proto-jets, from the dimensional transverse momentum fall off to a dimensionless quantity, the angular resolution that you have available to you. And it's natural for a normalizable theory with a conformal in it, in, again, what was, to me, far too sophisticated words for the time. So the idea was that if you have a picture that looks like this, two jets, most of the energy is going into cones, you let a little bit epsilon of the energy radiate out, and you should find a cross-section with no large ratios of Q over M, and this is what became known as infrared safety. So what one is doing is trading the high energy limit for the zero mass limit. Or I should say, this was all zero mass, but now the idea is let's go out and actually say, keep the masses fixed and, turn up the electricity on the accelerator. So there's a new class of observables, jet cross-sections. So I wrote a paper about this in 1975. We defined two states to be jet-related if they differ by the emission or absorption of a number of zero-energy particles, or by the transformation of one set of parallel moving particles into another. And this was 1975 preprint. This little thing will be familiar. This is what here is called the angular energy current. It's kind of a proto radiation pattern, energy-energy correlation if you have two currents. So energy flow then becomes the focus of computability. This paper was not accepted for publication, but in some ways that was my good fortune, given how it worked out. And anyway, actually, when I computed the darn thing, I had a log squared delta, but it should have been log delta log epsilon, so yeah, I didn't have to publish an erratum, look at it that way. So, but this is happy. It's like in tradition of gauge theories, slow discharge of a condenser. This is Poynting's original article, and it looks just like the LEP data, The slow discharge of a condenser was what Poynting talked about, but the fast neutralization of a colored dipole, that's what LEP was doing. So how this idea became known, a little bit of my own story, well, okay, it's like this. Jim Carrizone of Carrizone-Appelquist was at Fermilab, came and gave a talk in Urbana. And we talked. Then he said, oh, you should come and give a talk at Fermilab. So I did. Who was there? Tom Appelquist. He was on sabbatical. And he heard my talk, and he reported about the work at the Coral Gables conference the following January, which is January of '76. And that's why I got a second postdoc, because I didn't have a paper on the darn thing. And well, it happened because my advisor was there, and after Tom Applequist's talk, he got up and said, this guy Sterman's looking for a postdoc. It worked. So I got a postdoc at Stony Brook. So I was at Stony Brook for a while working on this subject, and then Steve Weinberg got the idea on his own, of course, in Slack. And he called around and said, anybody work on this ME goes to 0 in QED? And Kinoshita had seen my preprint, and he said, this postdoc, Sterman, at Stony Brook. So he called, and this was like about a year later. So this led to a phone conversation between me and Steven Weinberg, and to the paper Jets from Quantum Chromodynamics. So the zero mass limit was taken as a diagnostic for perturbative calculability, and that's playing off Q over M. M goes to 0 or Q goes to infinity of fixed M. Now, oops, I spelled his name wrong here. But Steve said to me over the phone, if we join forces, I believe we will succeed. In fact, it turned out to be a little more complicated than we anticipated. And here's the article, here's the letter we got back. It said, while some of the referee's comments were favorable, we cannot accept your paper on the basis of material now at hand. If you wish to reply, the paper will be given further consideration. Well, that was sort of surprising, and I dare to say it's probably the only experience like this Steven Weinberg had. And now, happily, a physical review letter is reconsidered after the acceptance of papers by Edward Farhi inventing thrust, and Howard Georgi and Marie Machacek inventing sphericity, both listed as received on September 26th. See, this letter was September 12th, and then they were accepted by physical review letters, so that kind of forced the hand of the journal. And after that, Basham et al. On radiation pattern and energy correlations, 1978, and a number of other papers followed shortly after that. So what is infrared safety? So it worked out, it got published, so we were lucky. So basically, quantities are predictable. This is the claim. Of course, it's not a mathematical proof. If they're finite in QCD perturbation theory and the perturbation theory is sufficiently convergent and non-perturbative effects are not obviously dominant. And this comes from Derulia, Ellis, Floratis, that's John Ellis, and Gaillard in 1978. Now, in some sense, this has become updated as QCD perturbation theory gives self-consistent predictions for some quantity C when C is dominated by short-distance dynamics in the infrared regulated theory and remains finite when the regulation is taken away. A contemporary update, or a kind of aspiration that we have, is that an infrared safe quantity C happens when C can be computed directly in 4 dimensions. And that, to some extent, is the aim of work that's going on now. It was kind of reviewed in this interesting paper, Torres Bobadilla et al., 2020, 2022. I think it was called May the 4 Be With You, which I thought was kind of cool. And then work I've done with Babas Anastasiou, who will perhaps touch on that in his talk. So I should say, infrared safety is great, but it's not the only concept that leads to consistent perturbative analysis. In particular, I point to parton-hadron duality, which is really built into the event generators we heard about from Torbjörn, saying that you can go almost to the point where your partons are on shell and then find a rule to switch them into hadrons. And you can even just sort of do it locally in momentum space for many purposes. So it's much more than jet cross-sections, but jet cross-sections do lay at the very bottom here, they lay the groundwork. And at the Tevatron, especially the LHC, they become a ubiquitous tool. So the work in particular I point to is of Salam, his collaborator Soyuz Kachiari, on identifying the best way to isolate jets in very, very complicated circumstances, and how to get quantities which you can calculate systematically. So here, just to show them, this is 8 GeV data, the jet cross-sections falling over 10 orders of magnitude, and it can be followed by lowest order or next to leading order calculations, and here the kind of range of data and experimental uncertainties that one has at 13 GeV data. One of these is Atlas, one from CMS. So where does it all come from in the last 5 minutes? Now that I'm halfway through. Well, you know, but that was the fun part, was the story, I think. So what is this all about? I mean, how does this actually happen in perturbation theory? So let me try to give you at least my understanding of how one should think about it. Infrared logarithms arise from coalescing mass shell, that is k squared equals 0, poles in loop integrals. These I would go by the name of pinches. It's just two singularities meeting at a contour. So to analyze these, you use Landau equations. It's all from Eden, the analytic S matrix from that old historic period before QCD became QCD. Well, it's still relevant. And what we do, or we're looking for observables that are insensitive to these pinches, which really depend upon the masses of the particles involved. And the basic finding is this, which is in a little bit modern terms. Long distance behaviors, infrared logs, places where alpha S of mu will get large, they are associated with classical propagation in the massless theory. So when the quantum finds and it sum overstates the classical motion, that's where the integrals get big, corrections get unsupportable and unsummable, and that's what we're trying to get rid of. So we work very hard to see where it comes from, but it comes out in all of the kinds of high energy cross sections that we're talking about here. It comes about in a very, very simple way because of this correspondence of classical propagation in the massless theory. So here comes a gluon, it comes in, it breaks up into two gluons. Who can tell? Because they're right on top of each other at these points where we get the large corrections. So these configurations, this quantum equals classical, are extremely restrictive at high energy, or large momentum transfer should have been what I should have said. And here they are. These are the basic processes that you can have. For lepton, antilepton, particles are created at a point, and they just propagate out into the future, where these lines now are not just one parton, but any number of collinear massless partons. So every black line then is, in terms of that I talked about before in the old paper, those are all jets. Okay, they're all jet-related states. They could be any number of final states. And so this is the only thing that can happen. From a point, emerge jets, that's it. We'll get to the zero momentum stuff in one slide, and that'll be as far as we're going to go. So anyway, in lepton-hadron, here's our DIS. We come in with a single parton, a single hadron, which is kind of spread out, but one of those partons is hit at short distances by absorbing the photon. And from that point, particles in the form of jets, jet-related particles, emerge and go in different directions. Because they're going in different directions at the speed of light, they can never come back to locally exchange momentum anymore, because they're just receding from each other at the speed of light. And in hadron-hadron collisions, again, if there's only one hard scattering, and we know, of course, that you can have a number of hard scatterings, but a hard scattering is like a precious thing. It's very rare that two partons come that close together. So usually it only happens once at some very large momentum transfer, and again, out come these jets. And these jets are emerging from the hard scattering in different directions at the speed of light. They can never communicate a finite momentum transfer between themselves again. Well, of course, in in gauge theories, these classical processes where the quantum equals the classical, giving large uncontrollable corrections, are addressed by soft vectors, and this is really what makes it, technically tedious to analyze. So let me just, I'll wrap up this talk with a little bit more about how jet cross-sections impose locality. And this is something that people were really thinking about at the time. How should we think about these final states that we get in deep elastic scattering, or down the road in hadron-hadron scattering? So for leptonic annihilation, for example, leptonic annihilation, E plus E minus goes to hadrons, we have the equation. We say, oh, well, we have two electromagnetic currents. That's what mediates the production of the quarks coming out of the QCD vacuum, and then there's, the annihilation of electrons themselves as an overall factor. But here I'm just showing a trace of the two electromagnetic currents. But in between the two are the final states, all the hadronic final states. It's all pions, protons, whatever. On the other hand, the sum of these ends is just 1. And so we end up with the optical theorem that says the total cross-section is proportional to the imaginary part of the forward scattering amplitude. But now we say, okay, this left-hand side is full of long-distance information about how the partons were produced. There was radiation. They turned to hadronized and all this kind of fun stuff. On the right-hand side, we say, well, let's look for some large correction. And on the right-hand side, we can't find it, because it's a time-ordered product of two currents that are close together in configuration space, and there's no classical path from the point X to the point 0, which is on the light cone. The classical light cone paths just go off, and they can never come back to the other J. So the thing is short distance, okay? And that's what makes it work, because the theory is making itself short distance. How did it make it? Because we asked for the total cross-section. It was our decision. Okay? On the right-hand side, no classical pictures. So what we're probing the vacuum at short distances imposed by the Fourier transform. The currents are only a distance 1/q apart, even though every single parton hadronized. What about, okay, that's nice, right? And people accepted that. We're very comfortable with that. Well, what about jet cross-sections? How should we think about it in this language? Well, here, we can't use the same unitarity, because our cross-section, E plus E minus goes to jets, has this theta function that says, I'm only going to count this darn thing if it's got two jets, and if it doesn't, I won't count it. So now I don't have the sum n equal to 1. But, okay, here's what we can do. Each set of jet-related states, I'm going over, all right. Well, no, I haven't gone over all 50, And this is really the culmination of the talk here, is each set of jet-related states has its own unitarity, okay? And you can prove it, and here just, of course, can't go over in detail, but here we have, say, in light cone-ordered perturbation theory, which Stan was talking about, we have an amplitude, a delta function that says this is the state we're looking at, and then we have the complex conjugate amplitude. And in each one of the terms, as we sum over all light cone orderings, if we sum over these delta functions, expand them into the 1/+ I epsilon minus 1/- I epsilon, a kind of reversed unitarity it's sometimes called, what you end up with is the difference of two expressions with one with only plus I epsilon, the other with only minus I epsilon. And you're back in the situation where you can't find any pinches, because everything is either amplitude or complex conjugate amplitude. So summing over the jet-related states removes all the pinches, and with it, the long time behavior. The two currents are drawn together, not because of the optical theorem in the full theory, but because of the optical theorem in some sense in an effective theory, which we'll be hearing about also later. It all has to do with the measurement that we make, or the set of measurements that we make. This sometimes goes by the name of, especially nowadays, of local unitarity, and it has many, many applications. In fact, I'll wrap it up by just showing one of the applications. Oh, well, you can see what I'm, oh, well, it looks nice, right? Hey, this is, I mean, you know, this, I would say, if there was a time where QCD was just undeniable, it was after Mike Kreutz's work in '79, but the three jets, well, sort of like the Petro results, that was great, but really UA1 and UA2, I think UA1 was first, to get these things from SPS at CERN, where you really saw those quark jets coming out. There was just, beyond that, it was, QCD really changed from plausible to absolutely undeniable. Well, having said that, 50 years, QCD is still young, okay? Many original issues remain from weak to strong QCD, and this is really pulling back from saying we want something that's totally short distance dominated. Well, because that was our choice, how we measured things. We can make other choices. We can allow those currents to come a bit apart and ask, what are the details of the final state as that happens in that set of events that we select? And in this way, we hope systematically to look at the actual dynamics going away from the shortest distances. This is the kind of thing, and using this local unitarity that I talked about before. And here, a general form, if we weight states, for example, by some function, not just 0, 1, in other words, it's one is function, so I give it 1 if it's a 2-jet, I give it 0 for everything else. That gives me the 2-jet cross-section. But I can get any weighting of states that I like. And in doing so, you can rewrite things that in a way that superficially at least satisfies that criteria for infrared safety, which is that it's integrable in 4 dimensions. So you get, this is a form for such a weighted cross-section derived by Aniruddha Venkata and I recently, and hopefully it will appear soon. It's just a sum over many, many contributions from each state, but all of the contributions can be shown to be integrable in 4 dimensions. Okay, and so really, it's the last 2 lines wrap up the talk. They're unprecedented computational concepts and capacities that are still to be exploited, where one can really think about using our imagination to get the kind of weights we want for final states. And the extraordinary experimental and theoretical developments make the dream of mapping the paths between partons and hadrons a possibility. So thank you.
Thank you for this beautiful talk. Are there questions, comments?
Okay, I'm going to do the rest of the slides, so that'll show them. No, it was an empty threat.
Thank you, George. It was a very nice talk. So I will bite at the bait that you put at the bottom of this slide. How do you get started mapping the path between partons and hadrons? What's the first thing to do theoretically, and what would you like to know from the experiments?
Well, I think that this is something that's going on now, where the experiments are giving more and more data. There's improved ability to identify hadrons in the final state and to calculate correlations. So a lot of work, some of which we'll hear from Ian Molt, for example, about energy-energy correlations. That's the energy flow part. But also, Kyle, who's here, and Ian have written a paper where they're talking about the correlations, not just in terms of energy flow, but also with charge. Here, we have predictions given by the event generators that we just heard about recently. And so taking measurements of things like that, the relationships between not just the energy flow currents, but the energy flow weighted by charge, flavor, in ways that, no, I don't have a detailed list of things, because this is relatively new thinking for me as well. But I think there's a tremendous potential there. Let's see where, for example, the Lund string model works, or how it might fail as we begin to look at detailed correlations inside jets. And the abilities that experiments, especially now the LHC experiments, for particle identification and momentum measurements, I just don't think that theorists have realized yet fully what a wealth of data we have available. And also we have tools where there are benchmark models to compare to. Now, who knows, maybe it'll work out. You know, we may discover that Pythia was right. Yeah, not a chance, okay? But, you know, there's like hope out there. Oh.
Well, the question I would like to ask is kind of quantitative question rather than qualitative. Let's say we consider a total hadronic cross-section and a plus or minus annihilation. It's the most inclusive quantity which you can imagine. Let's say the total energy of this electron-positron pair doesn't go to infinity, but let's say 4 GeV. Okay?
Well, that's what we had.
Yeah, that's what we had. So if everything was as smooth as you described, and you calculate the Parton cross-section plus gluon emission, introduce all infrared cutoff, then you get a smooth curve, right? Theoretical prediction goes with a smooth curve for these most inclusive processes. But if you do measurements which are precise enough, you don't see a smooth curve. You see till the energy 4 GeV or so, you still see oscillations, which are due to broad resonances, highly excited states. So, okay, you might say that it's almost a smooth curve, but it's the question of accuracy. When the Parton prediction becomes a smooth curve, which we can call honest to God's jet. What is the energy? How can you predict when this transition from not so smooth into totally smooth?
Well, okay, let me try to at least address, I mean, clearly sitting right at the JSI or something, already excited. But partly that's the point. The big peaks that we see around there, if I'm remembering right, are really associated with charm.
No. Let's say forget about charm. We have rho prime,
then I
rho
have to...
double prime, and only the rho peak is really conspicuous. The next peaks, the next is 5% or 10% of the rho, the next is 3%, but still, you see them with your naked eye. Mm-hmm. You see that this is not the smooth curve you predict in Parton Gluon calculation. So let's say you want to make a statement. The worst, if you consider not the totally inclusive, but let's say you want to separate 2 jets, one and the second, or 3 jets, even worse, then you, in order to really to get to the domain where you have a smooth picture, you have to go maybe to 20 GeV, maybe more. But my question, I'm not against this. But my question is, at which, let's say I want 0.5% accuracy in the prediction. How far, can you say beforehand, how far in energy per jet should I go?
What I'm saying in this, really, is that as embarrassing as it may be, I'm saying that's the kind of question we should really think about asking now with the kind of data that we have. Let's go out and find an energy, maybe an E plus, E minus. Well, we can go out, where it is really asymptotic, where it really is smooth, and where, well, we saw that plot in R. I mean, there is a place where, you know, perturbation theory goes right through it. But then to ask, okay, let's now creep down and try to understand the way in which this fails.
Okay. So
And it's exactly those things. And what do we have to add to perturbation theory to do that? First of all, of course, I've been saying all masses are the same, you know, but it's really just the U and D quark that really have small masses. But then there's the mass associated with chiral symmetry breaking. And for goodness sake, where do we begin to see that begin to show in event shapes or in total or partial cross sections? Could we start to ask the questions of how are we deviating from the part-time model, and what are we seeing when we're doing so?
Thank you. I understand that you are saying that 50 years after the creation of this paradigm, we still cannot answer this question. No?
Well, we don't have a solution to the three-body problem either in Newtonian gravity. But tremendous strides have been made in addressing questions like that.
Energizing review, but my point is I tried to emphasize as yesterday that whatever we can do in Euclidean, when we transform it to Minkowski, it becomes many orders of magnitude harder problem, because in Euclidean exponentially small correction, if you analytically continue to Minkowski, it becomes a slow power
Oscillation, yes.
Okay.
Okay, our next
Misha,
speaker.
Misha, let me take this. This is perfect, I think, for the reception we have later. Let's thank George again.